Thank you for having me here. That's a very special opportunity for me to be presenting something to an audience of people whose faces are quite known to me. This is not very usual, but this is very special for me. As already said, I've been honored twice this year for having done something in the past 20, 25 years, not only research, but also educational activities, teaching and supervising students. So I'm really happy, and it's also a challenge for the rest of my life to do something more. Dark side of modern AI. Okay, I'm not going to talk about ethical and ecological problems associated with modern AI, as you may have expected, but more conceptual, or I would say cognition-related problems with modern AI things. And that topic, adversarial vulnerability, is a piece of that talk. So let me go to the next slide. So I'll try to prepare a cocktail of things, given the heterogeneous audience here. So that's in a nutshell in the top left corner. So something more general, less technical, and then two pieces of recent research done in collaboration with 3 PhD students. So, you know, during the last many years, I've interacted with many people, and I had to select something. So I'll be talking about some recent results that are related to, you know, negative or shortcomings of modern AI. So the graph shows, in a nutshell, you know, how the field has progressed during the last 70 years, starting with symbolic AI and now culminating with sub-symbolic, neural network-based methods that use training in deep networks. So the relationship between these concepts is shown on that circular graph. So now we are in that period of sub-symbolic AI hype over 10 years. Again, in a nutshell, we can say that many tasks have been solved, concrete tasks with standard methods, having huge data sets, large computing power, etc. And what we've seen also that in quite many cases, the AI model already surpasses human performance. It's doing better on a concrete task. So that's a challenge. Why is that? What does that mean, actually? In various domains like image classification, language models, computer games, and others. Many of these tasks are supervised, so we have labeled data sets. We apply the modern ways of stochastic gradient descent training in order to minimize the error. And actually, we are looking for a function that can be seen as a composition of a number of nonlinearities that correspond to individual layers of deep networks that are, in many cases, feed-forward. Sometimes they could be recurrent. And, of course, good generalization is what we need. And there is an interesting phenomenon called double descent that has been identified that sort of clarifies why is it the case that modern models that are typically over-parameterized, so having more parameters than is the size of the data sets, is due to double descent, which means that we sort of have to reconsider the original thought of how machine learning works, that too much training leads to overfitting, etc. But according to this graph, we see that if the model has many more parameters than the data set, still, we can observe that the testing error decreases. And of course, the training error is already 0. So that means that, these huge models don't overfit. They just perform very well. And that's something that's kind of counterintuitive, I would say. So, over the last 10 years, there have been a number of milestones shedding some light on how these models progress. So, for instance, AlexNet, it's already outdated. Today, we have, by several orders of magnitude larger models that are applied to image classification. But back then, it was a kind of a big achievement that it won the competition on image data, ImageNet, etc. So, big achievement given the hardware. End-to-end training, so we don't care about any feature extraction, but just take inputs that are mapped to labels. In another area, like game playing, for instance, AlphaGo, you must have heard about that. So again, an AI-driven machine, trained by reinforcement learning in combination with classical AI, like Monte Carlo tree search, could beat the best champion in the world in a Go game whose complexity is extremely high, so to say. So again, there was some modeling behind that. but I will mention reinforced learning again in the context of our recent work. And last but not least, you all have heard about ChatGPT. That's something that was really remarkable, appeared almost 2 years ago. I'm sure all of you have maybe have had some interaction with that, or most of you. So that's something related to deep neural networks and providing very remarkable achievements. We know that it's a combination of supervised learning with reinforced learning. Michal in this morning very nicely expressed or mentioned these things. So something that has had an unprecedented impact on us, the society, because it's so easy to use, and it will have very strong, it's already having very strong consequences on the future and the society as such. Today, there are many more competitors already on the stage, so I mean they can now compete with one another, taking more and more resources. So again, ecological factor is becoming more and more important. But we know about the problem of these machines, hallucinations. They are not reliable, they're not trustworthy, because from time to time they cannot tell the truth, and it leads to, for instance, errors in reasoning, etc. So why do they hallucinate? Actually, we don't know. I was surprised to see there are so many hypotheses what could be behind that. Many of those are related to either data or training and other things. But I mean, there is a number of reviews out there that speculate about the potential reasons. And it could be that we maybe should jump out of the box and look at it from the outside, because what I will mention is the problem of grounding, that these models are completely ungrounded. And when I look at this from the cognitive science perspective, there is a nice kind of series of important milestones, for instance, starting with Turing machine, that was designed to test intelligence in machines by having passed the behavioral test of intelligence in a natural language by the terminal, that gave rise to the thinking experiment, thought experiment in Chinese room problem, whose sort of entailment is that mere processing of symbols in an unknown language, even though it looks intelligent from the outside, does not mean that the person sitting inside would understand. So symbol manipulation doesn't help. Therefore, in cognitive science, symbol grounding problem was presented or introduced, claiming that symbols have to be given meanings in some way, such that they could sort of give rise to some understanding. So that's how language, for instance, works in humans. In today's modern view, so that symbol grounding problem can be converted to the vector grounding problem, because in large language models, which are ungrounded, basically, they deal with word embeddings that are high-dimensional vectors that still, even though they are distributed vector number-based, they are still not grounded. So that's a self-referential system. So it's like if you were trying to learn certain language that they have in a dictionary, that one word is explained with other words. It's sort of circular. So you need to ground it, you need to anchor it somewhere. So things like this have been known for quite many years, because so-called distribution models of word meaning are or have been there since 1990s, that are the same idea as modern large language models. So now I'm changing gears, because I'm going to refer to our research that has something to do with problems of modern AI. The first one is related to two PhD students, Stevo and Iveta, who successfully defended their thesis this August. I'm happy that they joined our department. So we focused our view on the so-called adversarial vulnerability of trained neural networks. Even though trained models perfectly perform on the data sets, they can classify the images very high accuracy, sometimes even surpassing human performance, they still are sensitive or are sort of vulnerable. They're not robust, which means that they can be easily fooled by images that are very slightly perturbed. Something's changed, number of pixels, values of pixels, such that, I mean, humans would never be fooled that way, but these machines are. So this classical paper shows that you have an original image that's classified as panda with confidence. You add perturbation that looks like noise, but it's not an arbitrary noise, but it's a well-targeted noise based on, for instance, knowing the derivative of the cost function with respect to pixels. So you know the direction, how to change the pixel in order to increase an error and leading to high misclassification. So, I mean, this is what is the result. So to us humans, of course, both images are unquestionably pandas, not for the machine. So this is a fundamental problem for any safety critical applications, no-go. So this is not a solved problem because, of course, there have been some defenses designed or adversary training imposed, but it's like a chicken and egg. So you never have a universal or robust solution. So I guess that something fundamental has to take place in order to overcome this problem, maybe taking some inspiration from somewhere. And it not only applies to images, but also like malware detection or speech recognition or reinforcement learning. So therefore, we just wanted to understand what's going on in trained networks such that they start misclassify for some reason. There must be a mathematical explanation, and that's what we did. So like taking different neural networks, like on MNIST or Cypher10, feed-forwards are either fully connected or convolutional, or VGG type, whatever. And here you can see some examples of pairs of images where the one on the left is the classical, the other one is the adversarial, and these are the predictions of the class with the confidence. So you see how evident it is. And of course, when one talks about perturbations of original images, one has to take care about the metrics. So either you take L infinity metrics, which means that you can perturb each image to a certain maximum extent of epsilon, or you take L2 norm, such that the adversarial image versus the original, I mean, their distance cannot be beyond something. L1 analogically, and L0 means how to modify the minimal number of pixels with certain perturbation in order to fool trained model. Okay, so one has to. We did it. Actually, the students, they did all the simulations. I was just talking to them. So they've done a lot of simulations. Rubbish class examples. Okay, so something like this, for instance, is classified as frog. That's unbelievable, right? So it has some implications. Actually, what does the trained network actually know about the problem? Actually, it knows almost nothing, I would say. So what one can do is to look at like calculating the distances of adversarial images to individual classes. So if we have a number of inputs, like high-dimensional inputs, each being an image, so we can think of the so-called manifold. So each category is supposed to lie on a manifold, which is a nonlinear subspace of the input space. And so the question is, if there is an adversarial, how actually it behaves, because it goes from one layer to another layer to another layer up to the output. So that's a sequence of nonlinear transformations, and something is hypothesized to be taking place regarding those manifolds. I'll get to that. So I don't want to bother you with details here because there's no time for that, but just for you to show that if we calculate the distances, so like layer 1, layer 3, so for instance, we can see that if we calculate the distances of like adversarial images to either correct or incorrect class, so we see that their distance to an incorrect class decreases, which means that they are gradually attracted towards an incorrect class. If it's a targeted attack, so we want something to be misclassified to something concrete, so such a gradual transition or movement is taking place in that network. So that's what has been observed by some calculations and has been confirmed using a variety of methods. So for instance, in one method, when one considers, this is method 1, like using car nearest neighbors, like testing the class assignment, which is the nearest class for any like perturbed image. So one can do these calculations for one concrete example, for instance, like looking at like class original, class predicted. So that's a transition from one to the other for a specific network, specific attack that was assumed there. And you're looking at some ratios. I mean, how many nearest neighbors are from this class versus the other class. And when you plot this on the right, so this is for two types of attack. For the other ones, it looked somewhat similar. We see that all those curves like go down. So it means that sooner or later, these adversarials are attracted to the wrong class and they are then so predicted. So that's something that's inevitable. It takes place, even though it may start innocently at the input. It's sort of exaggerated or expanded somehow, emphasized later in the network. So that's just one method in a nutshell. Another one was related not to calculating these direct distances, but calculating the projections of the like tested inputs, like adversarials, to the manifolds, which were approximated by the convex combination of nearest neighbors, as shown there. So that's something that one can do, and remember the coefficients, these alphas, and then use the same alphas for the input space, where one can sort of do the similar thing. So this actually enables us to like monitor how the distances of adversarial change over the layers. Okay. I don't have time to tell us more details, but just the message in a nutshell. And there, again, like looking at concrete examples, how these inputs move. So the picture was quite consistent. And of course, one can also do some visualization, like nonlinear projection of high-dimensional inputs to the 2D in nonlinear way, like, for instance, using UMAP. And there, one can also see whether those adversarials are sort of overlapping or entangled within the original data or not. We can see the rubbish class examples are somewhere else. And another thing, what one can do with this is this entanglement. So there is this hypothesis, manifold disentanglement hypothesis, that sort of postulates that the process of classification has to be enabled, facilitated by the fact of unfolding the manifold, such that they could be linearly classified at the very end, because that's what the last layer does. Okay, so this was done here. Using this formula that sort of tries to preserve, so to say, the relative distances of points across two different spaces. Of course, there's some information has to be lost because of high reduction, but basically what one can see that those top curves, the entanglement decreases, which is indicated by lower values. So that's this in a nutshell, and in the remaining time, I have like 8 minutes, I guess. I started later. So I would refer to another piece of work that was done with a student, a former doctoral student, Matej, who defended his thesis last year. And I think this is a valuable piece of work because like 2 years work associated with a lot of pizza, beer. Because, yeah, we had a lot of discussions, but Matej and Michal, they did all the simulations. That's from another domain, but it's about reinforced learning, deep reinforced learning, because there exist tasks, sequential tasks, when the agent has to learn something meaningful, to learn the policy, such that it can do something, but despite very sparse reward. It's like as if you wanted to learn chess by just learning that you just lost, knowing the moves, but not knowing which one is the best. So it's a very difficult thing, and especially in game playing, that's very sort of attractive. So if this external reward is very sparse, that's very difficult for an agent to learn anything, because it's just acting, not knowing how good it is, or it has been. But the concept of intrinsic motivation can help. That's something that also drives our lives. We also take advantage of internal motivation. For instance, the curiosity signal is something that's not directly externally rewarded, but it's internally rewarded by our brain. And that's, I think, very good, because that's something that has been adopted also in the literature here. So think of something that, how can we derive that the source of intrinsic motivation, or like internal reward? And actually, the concept comes from these network distillation methods. So, it started with random network distillation. Here, we introduced the self-supervised network distillation, which turned out to be a much robust, much better way of how to prepare the agent to learn like how to play a game, computer game, that it takes like input frames, has to map the overall observation into an internal feature vector, Z, A, etc., And of course, there's this target network and the learning or target model and the predictor model. The predictor model trying to approximate the target model, and the differences in the feature vectors between the two serve as a source of internal reward. That's something showing that, oh, so the predictor network is taking or has observed something that has not been visited many times, therefore prediction is worse. So it's like curious, I'm learning something new, so I want to improve, and I take advantage of that intrinsic motivation signal that's actually added to the external reward. And the combination of the two is then used in the framework of overall learning. So, yeah, maybe that slide might be redundant for many of you, but I think that the general audience, some people have not encountered the reinforced learning. So it's a formalization of sequential problems based on Markov property. There's a state space, action space, transition function, like going from state to state. The agent is trying to learn the optimal policy, like doing the best act in every single state, such that it maximizes the expected long-term reward. That's the goal. That's how it can be formulated. There's also the state value function that learns to predict the long-term reward, that V. And in our models, for instance, this was this deep network that was predicting both the policy and also predicting the internal and external reward, like with separate heads. Okay? Feed-forward network, convolutional. So yeah, so this is in a nutshell the whole graph. It turned out that this allowing the training of the target model along with the predictor model led to very much more efficient organization of the feature space. The quality of the feature space can be measured by, the overall volume. So like you have 512 dimensions, which is a reduction from several thousands of original dimensions. So that you want to take that volume as much as possible. So you need to enforce expansion along as many dimensions as possible. So that can be measured by, calculating some eigenvalues that like having this Gaussian volume. And so the story is more complicated. Actually, the overall cost function is a combination of several both like cost terms or regularization terms that are sort of whose roles are different, but actually what we need is, for instance, to make sure that if we have two consecutive frames in a game, they don't differ very much. You want to have that they have the similar feature representations, right? Like to preserve continuity up on the mapping. And of course, if we have two different frames, that's what we can do because we can do some rehearsal, like storing those and making them like dissimilar. So we want to preserve the dissimilarity. So there are things like this that all, in a combined way, tricky, hyperparameter tweaking, etc., gave rise to very robust behavior of the three versions of that S&D that were done. And the evaluation, there's a number of tables, but I didn't want to overload you with some numbers. Pictures are nicer, I would say. So like what you value the score, how much you have played in each game. So like in these 9 environments, it worked better compared to baseline. One game was too difficult, like Pitfall. No way. Maybe the most complicated, but so the training of the model involved this minimizing that cost function that was there with Adam, combined with reinforced learning using PPO, which is a standard reinforced learning algorithm. So we can see that those curves grow. There's average score per episode. So we see some growing profiles. And environments, they are shown there. So we take like 4 or 2 consecutive frames to have some context. And I don't know, there are some other technical details. The simulations took like hours, long hours each run. I don't know exactly. So yeah, one can also look at some insights. So if you have a trained model, we want to understand, what is it doing? So for instance, like tracking that one on the top, so you can identify interesting points. This was when the agent managed to go from one room to another room, like to have some behavioral correspondences of the trained model, or for instance, at the bottom, like how well the two models can organize the state space or the feature space. Okay. So, yes, I'm going to the conclusion with good timing, I think. So what did I try to show you? Yeah, that's obvious that AI has progressed nicely over the last decade. There are many successful applications. Almost all of them have something to do with deep learning in a respective model. Still narrow AI, very focused. Of course, artificial general intelligence has been pursued over the last decade. So that's the major challenge, right? To make a universally learnable machine being able to do everything. But it's still difficult. These hallucinations is something that has to be solved. Adversarial vulnerability is a fundamental problem that has not been overcome. And regarding those image classifiers, so yeah, I would say that they cannot really see. I mean, they completely differently see compared to humans. We definitely have conceptual representations of object categories. We know what dogs are, cats are. These models don't. They can just discriminate the classes, and that's just like a imitation, not even an imitation of certain cognitive ability. Regarding reinforcement learning models, yeah, there's been a lot of achievement, but still they are so greedy. They need so much training, and of course they are also vulnerable. So yeah, that's the question is how to improve this. And in a nutshell, we can say that there are so many differences between deep learning models and human cognition. And I believe that some inspiration could be taken from cognitive science when it comes to vision, when it comes to language learning. For instance, the notion of grounding, that's been already done. I know, like multimodal deep learning, large language models are there. So trying to look at some correlations between modalities, that's a question whether learning correlations is sufficient for learning causal relations, because that's not the same thing, of course. So I think I have done my job, and I want to thank you for your attention.